In this video, we will show how to compute the DC electric resistance of a wire of square cross-section. Now, this procedure applies to any geometry, but in order to compare it to an analytic value, we will use a constant conductivity of 10 to the power 8, a length of the wire of 1 centimeter, and a square cross-section of 1 millimeter side. And using Pouillet's law, we should get exactly 100 micro ohm resistance. So let's create our project and draw this wire. Let's make the wire aligned with the X direction, 1 centimeter long, and a square cross section of 1 millimeter side. There we have it. We can magnify it to see it again, and we can move on to the materials definition. So we pick aluminum, but what we really are going to do is override the electric conductivity with our exact 1E8 conductivity to get the same result as these 100 micro ohm. Now the whole geometry is made of aluminum, so we pick the whole geometry. Then we go to the physics, we add the physics, here the current flow. In steady state, it applies to the whole volume, so we don't have to pick it. Then we apply a constraint on the right surface with 0 electric potential value. And then, in order to compute the resistance, we need to know both the voltage on the left side as well as the total current flowing in. So we'll add a lump interaction, and we will add it on this surface. Now, to get the resistance, we have to divide the voltage on this side minus the other side, but the other side is 0. So the voltage on this side by the total current flowing in that side. So we could provide the voltage, and then after a simulation, we'll get the total current, we'll divide, we'll get the resistance, or we could alternatively provide the total current flowing in, let's say 1 amp, and then after simulation, we'll get the voltage at that electrode, and we'll divide, we get the same resistance. So both ways are possible. Let's choose this way here. Now we are done. We can move on to the simulation. We can mesh. We could refine just a little bit the mesh, although in this case it doesn't matter because the solution will be captured exactly down to machine precision. Of course, if you would have a curved wire, this would be a different story. You would have to refine to get an accurate resistance calculation. Now we could already ask for the outputs if we want to see, for example, the electric potential V for visualization, but we want to actually compute the resistance. So what we will do is add a custom discrete output, and there we will have access to the V, the potential on the left electrode where we define the lump interaction, and also to the total current flowing in. So the resistance is nothing else but this divided by the total current flowing in. That's it. Now the meshing is done. We could visualize it, and we'll see that it's very coarse. But here, because the electric potential will decrease linearly from left to right, this is actually enough to exactly capture down to machine precision the solution. So we run this extremely small simulation with 1 core, and we can check the logs, and in the logs will be displayed the resistance value. Now there we have it. So down to machine precision, it's 1E minus 4, though that's exactly our 100 micro ohm resistance. Now if we want, we could as well visualize the electric potential field V, and there we have it. So indeed, there is a 1 amp current flowing from the left electrode to the right electrode, and the potential on the left electrode is entirely defined by the fact that we have assigned a 0 volt on the right side and a 1 amp total current flow on the left side. If we had assigned 1 volt lump forced value on the left side, then we would see 1 volt here, but then the current would have would be such that it satisfies 1 volt on the left and 0 on the right, but the resistance value would have been exactly the same. Thank you for watching this video, and see you in another one.